chemistry in year 12 organic
Recording in
chemistry.
progress.
So the basics that you need to know for year 11 organic chemistry. All right, in year 11 organic chemistry, you pretty much just do two different types of substances. You do hydrocarbons, which only have carbon and hydrogen. And the other one you do is what we call alkyl halides. That's basically hydrocarbons with some chlorine or fluorine or bromine or something in them, okay? But pretty much you exclusively did hydrocarbons. Now, how can hydrocarbons be classified? By the way, another way that some people call alkyl halides, they call them haloalkanes or haloalkenes or haloalkynes, whatever. I'm just gonna write alkyl halides. All right, so for hydrocarbons, what are the classifications of hydrocarbons? Hydrocarbons means has C's, H's, and nothing else. Whereas in year 12 organic, we have O's and N's and other stuff, C's, S's and whatnot in it, okay? So there are two types of hydrocarbons. There is aliphatic and there is aromatic. Aromatic simply means contains the benzene ring. It means contains the benzene ring. Whereas aliphatic means that you don't have a benzene ring. So what are your different types of aliphatics? There's alkanes, alkenes, and not strictly part of the course is alkynes with a triple bond. All right. And then guys, what specific phrase is used to describe alkenes and alkynes? Unsaturated. They are classified as unsaturated hydrocarbons. Whereas what is alkanes? Because they've got the maximum number of hydrogens that can attach to them, they're classified as saturated hydrocarbons. Now, PS, even benzenes, despite not being able to do addition reactions, they're also classified as unsaturated. All right, even the benzene rings are classified as being unsaturated. Next thing you need to understand is this. You need to understand that obviously you need to know nomenclature, how to name stuff, okay? You need to know how to name stuff. And when I say nomenclature, you need to know how to name them in all forms. So guys, how can they exist? They can be straight, or they can be branched, or they can be cyclic. Okay. You need to understand how to name them. You need to understand their generic molecular formulas. All right, so what I mean about that, guys, alkanes, what are your different types of alkanes really? They can either be straight or branched. And if they're straight or branched, what is their formula? CN, H2N plus 2. All right, you should remember this from year 11. Alternatively, what can alkanes be? Cyclic. And what is that formula then? CnH2n. So every time you go cyclic, you lose 2 hydrogens effectively. So that's a generic formula. That's alkanes. So what about alkenes? All right, alkenes can be again what? Now guys, when I say alkenes, I mean alkenes, but just the one double bond. Because technically you can have 2 double bonds and it still counts as being an alkene. So I'm assuming I'm an alkene with 1 double bond. Then what else can it be? It can be straight or branched, just like before. And what's the generic formula if you only have 1 double bond and you're straight or branched? CnH2n. And what if you're cyclic? CnH2n minus 2. All right, so that's how it works. But be very, very careful. But because you could technically have, you just have to be super careful. So what I mean about super careful, if someone gives you something in the form CnH2n, it can be so many different things. What could it be, guys? It could be straight or branched. It could be a straight or branched alkane. Or, cyclic alkane. It could be a cyclic alkane. Or what else could it be? And straight or branched alkene. But how many double bonds though? Just the 1 double bond only. So what if someone told you that something is CnH2n take 2. What could that be? It could be alkyne. Yes. What else could it be really? It could be a cycloalkene, but one double bond only. Or it could be a straight or branched. It could be a straight or branched alkene with 2 double bonds. So you can never assume. Okay, it could be any. The moral of the story being, every time you do a cycle, you lose 2 hydrogens. Every time it's cyclic, you lose 2 hydrogens. Or every time you do a double bond, you lose 2 hydrogens. Okay, so just make sure you know your molecular formulas of them. What else do you need to know? You need to know your isomers. There are 2 types of isomers that we need to know. There are structural isomers and geometric isomers. What are geometric isomers also called? Cis-trans isomerism. So what does structural isomers even mean? Same molecular formula, but different structural formula. Same molecular formula, but different structural formula. All right, what are the different types of structural isomers that you should know? There are so many different structural isomers that you should know. One is called, they call it a chain isomer. I'll give you an example of a chain isomer. 1, 2, 3, 4, 5. Fill it up with H's. All right, as opposed to 1, 2, 3, 4, and put a carbon here. All right, what's the name of the 2 different things? This is pentane, whereas this is not 2 because there's nowhere else it can go. So methylbutane. All right, and these are chain isomers because it's just a completely different chain. One's a butane and one's a pentane. So there's chain isomers. There's also what we call position isomers. Here's an example of a position isomer. 1, 2, 3, 4, 5. Put a carbon here. 1, 2, 3, 4, 5. Carbon here. What's the difference? This is 3-methyl pentane, and this is 2-methyl pentane. Same chain. The only thing different is where the position of the functional group was. All right, so that's position isomers. What other type of structural isomer is there other than chain isomer and position isomer? Chain isomer, position isomer, there's also functional group isomer. E.g., what's this? Double bond here, and then fill it up with H's. 1, 2, 3, 4, 5. What's this? But, 1-ene. Whereas, what's this? What's this meant to represent when you draw a square? Cyclobutane, right? They're both C4H8 at the end of the day. They're both C4H8.
So doesn't alkyl group count as a functional?
Yes, this counts as a functional group. Yeah. Yes. So it's like the most simplest of functional groups. Yep. So far, so good. Are these completely different like functional groups? One's an alkene and one is a alkane, but they still have the same molecular formula. So that's another example of structural isomer. You can have functional group isomer, chain isomer, position isomer, functional group isomer. Okay, all different types of structural isomers. And then you can have geometric isomerism only in what? Only in alkenes. You need to have an alkene to have geometric isomerism. So it's the, basically they have a different geometric formula. Same structural and same molecular and structural formula. Same molecular and structural formula, but different geometric formula or different geometric configuration. Different geometric configuration about the double bond. there are two requirements for something to have cis trans isomerism. You must fulfill two requirements. Requirement number one for geometric isomerism is you must have the double bond. No double bond, no geometric isomerism. And what's so special about the double bond? There is no rotation around the double bond. There is no bond rotation around the double bond. There is no bond rotation around the double bond. So that is requirement number one. It has to be an alkene, otherwise you can't have geometric isomerism. And on top of that, requirement number two is this. Requirement number two, yes, you already have the double bond, but it is extremely important. This thing only works as long as X does not equal Y and A does not equal B. That is the only way it works. X cannot be Y and A cannot be B. So this must be different to this, and this here must be different to this here. Otherwise, you can't have geometric isomerism. Okay, so for example, guys, that's requirement number two. Okay, that you need the 4 different things right here. Okay, how do I show that to you? You need to have those 4 different things: pink, blue, yellow, green. Okay, that's the requirement. So for example, something like this, I'll give you an example of how this works. This versus this. All right, so you need to understand how this works. What do they both at least have? One criteria is fulfilled. What's the criteria that's fulfilled? They both at least have the double bond. Everyone agree to that? They both at least have the double bond. All right, the difference is going to be here. The difference is right here. Look at this, guys. What's this carbon? What's bonded on one side? Hydrogen. And what's bonded on the exact same carbon? Another hydrogen. Are these the same thing? So therefore you can't have what? Therefore no cis trans isomerism here. No cis trans isomerism. All right, I know, I agree that this here is different to this thing right here, but doesn't matter. This has to be different to that, and this has to be different to this, okay? I don't know why I highlighted so much in green. It has to be different to this, okay? Whereas over here, check this out. So there's your double bond, so that's criteria number 1 fulfilled. What's on one side in H? And then what's on the other side, guys? On the other side, there is this. Is the pink and blue different things? Yes, that's criteria on one side you're fulfilled. And what about on the other side? Is this here different to what's on this side? Yes. So this is different to this. This is different to this. So what are you allowed to have? Cis trans isomerism. And the way that I've done it, have I put the H's on the same side? Ideally, I should have drawn it like H here, and drawn the typical bow tie shape. But since they're on the same side, which version is this? Cis. This is cis but toluene. All right. Whereas this one is therefore just but 1-ene. There is no cis trans version. So now you guys understand that certain alkenes do have cis trans isomerism. Certain alkenes do not have cis trans isomerism. You know the 2 criteria. All right. And then the only other thing you needed to know is their reactions. So what reactions do these things undergo? So what reactions, guys, will an alkane undergo? Substitution and combustion. They all undergo combustion. What about alkenes? Addition and combustion again. And what about benzenes or aromatics? Substitution again, just substitution and still combustion. Okay, got it? Now, what do you need to know specifically about benzenes? What's the way of drawing benzene? Like this, with a circle in the middle? What was the old school way? Did the old school way show alternating double bonds? So there was an old school way where they just drew like this, but that seems to suggest that the double bonds. What are these actually? Intermediate bonds. They're not too fast. Sorry, they're not single bonds. They're not double bonds. They're intermediate bonds. They're actually called pi bonds and sigma bonds, in case it comes up in multi-choice. Okay, there's pi bonds and sigma bonds. But the point is, they're not true double bonds, which means they don't undergo addition. What do they undergo? Substitution. All right, and in terms of speed of reaction, how would you discuss speed of reaction? These are slow, and you need what? And they'll still be slow, but you need what? UV. Okay? What about these reactions? How do you describe them? Fast. And do you know what you need for this? These are moderate. They're not slow, they're not fast, they're just moderate. And you need a suitable catalyst. And it's not in your course what that suitable catalyst is. Okay, but I've done enough to know it's like stuff like FeBr3 or AlBr3, but it's not strictly part of your course. So that, guys, is a summary of all of year 11 organic. Okay, that's what you guys did in year 11 organic. There was nothing, and you did some empirical formulas, but that's all you did. So we review that. Look, it even says, let's just check whether we got hit every dot point. Hydrocarbons are compounds that have carbon and hydrogen. There's alkanes, cycloalkanes, alkenes, yeah, whatever. Carbon can form 4 bonds. Yes, including chains and rings and multiple bonds. Yes. Molecular formulas can be written as structural formulas. Yes. Yes. Combustion reactions. Saturated hydrocarbons undergo substitution when UV light's present. Alkenes undergo addition reactions. Yes. Alkenes exhibit structural isomerism, and sometimes what can alkenes also have? Geometric isomerism. Excellent. You guys all know the formula for benzene, right? As long as nothing's bonded to it. C6H6. Okay, as long as nothing's bonded to it. In the presence of a halogen and a suitable catalyst, what will benzene do? Substitution. That's exactly what we mentioned. And then I said you need to know empirical formulas. Okay, perfect. So let's have a look at question 1 and 2.
Recording in progress.
All right, draw. Okay, question number 1. Explain why this formula is superior to this one here. This, guys, is called a semi-structural formula. Okay, there's full structural. I just want everyone to know the difference between all of them. So the full structural formula is this. All right, the full structural, they just call it structural formula, is this. All right, so CH3, so C in the middle, and then CH. Guys, why would it be CH? There'd have to be a what there? A double bond. So there's C, double bond to C there. Okay, so there's CH3, and then C, double bond to C, and then an H here and an H here. And then CH2. Another CH2. And then another CH3. I get a bit lazy and sometimes I don't draw the H's. At Perth Mod, you definitely have to draw all the H's, okay? H. Okay, so you draw this. That's the full structural formula. All right, what's very close to the full structural? The semi-structural, okay? And that's what they've drawn, okay, guys? They've given us the semi-structural formula. And the semi-structural formula, CH3, CH2. Well, you get the point, okay? This is the semi-structural formula, and this is the molecular formula. So then you can explain, guys, that the semi-structural formula is superior. Why? The semi-structural formula is superior to the molecular formula. For what reasons? One, it shows shows all atoms and bonds. And what's so good about showing all atoms and bonds?
So whether it's an alkene or it's not
Good. Allows identification of the type of isomer. All right. And when I say type of isomer, it basically tells you what the functional group is, but not just that. It also tells you what the position of any functional group or the position of chain. So it shows you the functional group present. It shows the position of the functional group, and it shows the chain type, whether it's straight or branched. Okay, chain type. So in this case, guys, C6H12 could have been a whole bunch of things, but what did it specifically tell me? It specifically told me that it was a alkene and not a cycloalkane. So that's one thing that it told me. What else? It showed me the position of the double bond. It showed me exactly the position of the double bond. And on top of that, guys, what did it tell me? That it's straight, not branched. So that's to get full marks. Straight, not branched. Okay, makes sense? All right. Question 2. This is a much easier question. It just says draw the structural formula. Okay, I'm being lazy and I don't draw the H's, but remember you have to draw the H's yourself in your school exam. Two, 5 trimethylheptane. 1, 2, 3, 4, 5, 6, 7. 2, 5 trimethyl. So another carbon here, another carbon here. 1, 2, 3, 4, 5. Another carbon here. Then fill it up with H's everywhere. B, 1,4 dibromoethane. Ethene. All right, so that's double bond. One's got a bromine on them, two's got a bromine on them, and then you fill it up with H's. It's interesting, guys, they should have said cis or trans. C, 1,4 dichlorocyclopropane. So cyclo is this, 1, 2 dichloro, so 1 chlorine. All right, now here's the thing, guys. At every other school and in waste, you're allowed to draw this. So you draw chlorine like such, 1, 2 dichloro. But at your school, I don't know why your school has different rules. You have to show every bond. No other school has that rule. So you got to draw C, connected to C, connected to C, connected to C. And then you draw like the H and the Cl. And then again, the H and the Cl and H. So at your school, you guys have to draw that. But in waste, you don't have to. All right, D, 3-methyl-4-propyl octanes. Octanes 1, 2, 3, 4, 5, 6, 7, 8 in a row. 3's got a methyl and 4's got a propyl. So that's 1, 2, 3. And then obviously in your test, you have to fill it up with H's and write H everywhere. I'm writing a dash, you have to write an H. Cool. E, transbutene. Now, guys, I suggest you ignore the trans to begin with and do like a working out step. Okay, so working out step means do everything without the trans. So everyone knows what butene looks like. We just discussed it today, in fact. Butene looks like this. Now, that's my working out. Now, my actual answer is draw this in the middle, like with your bow tie shape. Draw this in the middle with your bow tie shape. So that's C double onto C in the middle with a bow tie shape. And then what? What's coming off one of the C's? There's an H. And then CH3. And it said trans. So make sure that you have the other H coming off on the opposite side. I hope you guys saw that. I'll just color one of them for you so you understand what I did. So there's like the blue, for example, and there's the green, there's the yellow, and there's the pink. So draw it like this. That's the bow tie shape. You can see it looks like a bow tie. Okay, and you can clearly see that there's the pink part, there's the blue part, green and yellow. Cool. Next one, no, we just did that. Okay, so that's what they want in the test. Okay, that's the trans picture. All right, diiodopropanene. 1, 2, 3. Guys, I don't know why they're saying propanene. Where else could the double bond go? Nowhere else, right?
To show that the origin is common.
No, but that's just, I don't need that. If someone just said propene, then we know that the double bond always goes in the lowest number. And if they're telling me 2, 3, that means the iodine goes on the 2, and the iodine obviously goes on the 3.
I thought the origin was good with the first one.
Then they'd be called 1, 3 or 1, 2. So this is a mistake. They shouldn't be writing the 1 there. All right. You only write the number if it's necessary. I know exactly where the iodines go without them writing the 1 here. All right, we cool with that? So that should have been just called, yes?
In a test, if like you write a number unnecessarily, is it possible to?
In WACE, if you write a number unnecessarily, it's wrong because it's not the correct IUPAC name. IUPAC name means name only what's needed to name it. Okay? Some schools have this policy that, if you write a bit more, that's all good. But no, that's the whole point of IUPAC naming is to make sure that everything has one name and one name only. Okay, but yeah, fair question. But some schools will be like, oh, it's okay if you give me some extra info. But there'll be, for example, I mean, it's if the teacher says this and said name this, and if I wrote prop 1 in, majority of schools will mark me wrong. They'll be like, why did you tell me that it's 1 in? Okay, so I think it's risky writing a number when it's not meant to be written. All right, but again, depends on your teacher. Hex 2 in, 1, 2, 3, 4, 5, 6, double bond is after the second carbon. And what else is there? 2, 3, 4, 5 tetramethyl. 1, 2, 3, 4. 2, 3, 4, 5, and then fill it up with H's. So guys, because it looks so ugly, it makes sense to just put every second carbon up here. Cool. H. Diethylpentane. Diethylpentane. 1, 2, 3, 4, 5. Diethyl. Notice, guys, they're not telling you where the position is. Why? Because think about it. An ethyl can't go here. It just makes it bigger. It makes it a pent. The only spot the ethyl can go is in the middle. And it's a diethyl. So basically, you put another C here and there's another C here. And then you fill it up with H's. All right. They specifically didn't write 2 because can't go there. All right. I. Cyclohexene. Okay. So I'm just going to do it. Okay, hexene, so draw a hexagon. And then it says, then it says 3-methyl cyclohexene. So you do this. 1, 2 dibromo. Now, guys, you don't write these numbers. This is just to help you out. 1, 2, 3, 4, 5, 6. This is just to help you out. Okay. Now, now that I've got that, should be easy because it says 1, 2 dibromo. So the 1 and the 2 have bromines coming off them. So if the 1 and the 2 have bromines coming off them, bromine here and bromine here, okay? You don't write the numbers, that's just to help you out. And the 3 has got a methyl. So every other school will accept that. But at your school, you actually have to draw this. C, C. All right, bromine here, and everywhere else 2 H's. So at your school, make sure you draw this. To me, it just makes it look disgusting. That's what you're expected to draw at your school, because it always says draw all the bonds. Okay, perfect. All right, J. Cis, I'll do the cis parts later. Let's just do the working out. That's hex, 3-ene, 2,5-dimethyl. So C here and a C here. Now let's draw the bow tie shape. So C11 to C. And then helps if I showed where the H's were coming off. Cis. Cis means you put them on the same side. So I'm putting this H and this H on the same side. If I call them one H and the other H, you can see that I put them on the same side. Then what's coming off? Something that looks like this. Okay. C, C, C. It just looks weird. All right, that's on one side, and the exact same thing is coming off on the other side. All right, now run out of space. In your test, I don't know what you're gonna draw it, but you're gonna draw it like that. Okay. I ran out of space to write all the H's. If I did just keep it simple, there you go. Everywhere I got an empty dash, you're meant to write an H. That's what it looks like. So they're on the same side. Perfect. Next one. K, cycloheptene. All right, I'm just gonna do it the normal way. Cycloheptene. Notice, guys, they don't tell you where the double bond is. Doesn't matter. Obviously, it's after the first one. 1, 2, 3, 4, 5. Oops. Pointy at the top. 1, 2, 3, 4, 5, 6, 7. Yep, that's 7, double bond. And then it says 3 bromo, 2 methyl. Now everyone remember that's effectively, this is like number 1, this is number 2, this is number 3. Okay, or some version of that. So the 2's got a methyl coming off it. So CH3. And the 3's got a bromine coming off it. All right, in your school test, you got to show all the bonds. All right, remember guys, just like in the previous one, when there's a double bond in a cyclic thing, only one thing comes off it because it already has 1, 2, 3 bonds. Okay, but when it's a single bond, what do you notice it's got coming off? Oh, I made a mistake. Did everyone see the mistake here? How many bonds is that? 3. So I was just about to say that when there's a single bond, what do you have to do? Make sure there is 2 branches coming off it. When there's a single bond, make sure two branches coming off it, but when there's a C, two branches, two branches. But when there's a double bond, only one branch coming off them. Okay, so far so good. L, methylbenzene. Anyone know what that's also called? Methylbenzene's common name is toluene. All right, you can write that down if you want. Methylbenzene's common name is toluene. And you can put a circle in there. All right, toluene. Bromobenzene is the exact same thing, but a bromine coming off it. And trans, 1 bromo, 2 chloro. Okay, ignore the trans, just do the working out first. So 1 bromo, 2 chloroethene. So ethene looks like this, 1, 2. 1 bromo, 2 chloro. That's my working out step. And now it says trans, right? So trans means that we got to put the hydrogens on opposite sides and the halogens also on opposite sides. So that would be trans, 1 bromo, 2 chloroethene. Cool. All right, now it should be easy, guys. It's just naming. All right, find the biggest chain. That's the biggest. Even if you did this, it would be just as big. All right, you start counting from this side, 1, 2, 3. So does ethyl come first alphabetically? Yes. So everyone's writing 3 ethyl, 3 methyl, and then 3, 4, 5, 6, 7, 8, octane without a space. B. All right, biggest chain is this. All right, the methyl can only come off the middle. So what's the name? Methyl propane. I don't think writing 2 methyl is a good idea because the only spot it can come off is in the middle. All right, biggest chain is not this, it's actually that. A lot of people would have suggested that's the biggest chain, but it's not. Okay, what I've drawn right now is the biggest chain. All right, 1, 2, 3, 4, 5, 6, 7. It's a heptane. Doesn't matter which way I start counting from, I have to wait till number 4. So this is 4 ethyl heptane. D. That's the biggest chain. All right, if I start counting this way, what would the numbers be if I start counting that way? The numbers would be, if I did start counting that way, this way, the numbers would have been 1, sorry, not even 1, 2, 3, 4, 4, 4. And if I start counting the other way, what's the numbers? 1, 1, 1. If I start counting this way, the numbers are 1, 1, 1, 4. Now, what's the rule? You don't add them up. You only add them up in cyclic things. Okay, in a cyclic thing, the order of priority is such that the sum is the lowest. But this is not cyclic. So you just look at the first number. Who's lower? 1 beats 2. You only ever look at the second number if there's a draw. Is there a draw? No. What's the first number? 2. And first number over here, 1. 1 always trumps 2, okay? What if this was 2? Then what would you look at? Then you look at the next number and then you'd be like, all right, 2 trumps 4. So you don't add them up. When's the only time you add them up for priority? In a cyclic substance. In a cyclic substance, you're meant to add up all the functional groups, the positions, such that the sum is lowest. So the name of this, what comes named first alphabetically, chlorine or methyl? Chlorine. This is 1, 1, 1, trichloro. 1, 2, 3, 3, methyl. butane. That's it. E. All right, now this is interesting. It's obviously cycloheptane, right? And Aaron agreed one of them's a 1 and one of them's a 2. Doesn't matter which way. Either way, the sum is the lowest. Who's going to be the 1 and who's going to be the 2? What's the rule? The rule is, in a cyclic substance, first of all, guys, the sum has to, so if you want to write down the rules, in a cyclic substance, you want the sum of the functional groups to be the lowest. Sum of the positions to be the lowest. All right. So you guys would agree that calling this 1 and calling this 2 and calling this 1 and calling this 2 is the exact same sum of 3. So what if the sum is equal? What's the next thing you look at? The largest alkyl group. The largest alkyl group has priority. So the name of this is, that one takes priority. What comes first alphabetically though? Ethyl or propyl? Ethyl. So this will be 2 ethyl, 1 propyl. Cyclo, pentane. Cool. Next one. You need to find the biggest function group that includes the double bond. You need to, the largest chain that includes the double bond. You must include the double bond. 1, 2, 3, 4, 5. So that's pent. We start counting this way. 1, 2, 3. We got to start counting this way, so that way the double bond gets the lowest number. So this is 2, 3, dimethyl, pent, 2, in. There's a few kids that write cis. They're wrong. Because look, these are the same things. To have cis transisomerism, they need to be different. I mean, this is different to that, but this is the exact same as this. So there's no cis transisomerism. Next one. That's the biggest one. And remember, the double one gets the lowest number. Always double one gets the lowest number. So this is 1, 2, 3, 4, 5. Is this different to this? Yes. Is this different to this? Yes. So therefore, there's cis transisomerism. And since they're on the same side, it's cis. So G, the answer is cis. 1, 2, 3, 4, 5. So that would be pent, 2, in. All right. Who gets a priority? Double bond. All right. So look, there's 2 ways of numbering it. One way of numbering it is this. 1, 2, 3, 4, 5, 6. And another way of numbering it is 1, 2, 3, 4, 5, 6. That's the 2 ways you can number it. Either way, guys, was a double bond after the first carbon. If I do it the blue way, can you guys tell me what functional groups are coming off it? 1, and then when's the next one? 6. And for a cyclic thing, what did I say the rule is? The sum. So what's 1 plus 6? 7. All right, so that's not as good as going the other way, because what happens if you go the other way? If you do the red, what is it? I know you have to wait till 2, but what's the next one you have to wait till? 3. And what's 2 plus 3? 5. So who's got the lowest sum? The red way. Okay, I've done this lots and lots of times. I've Googled it. Definitely for cyclic things, the sum has to be the lowest. Okay, so what's the answer therefore? 2, 3. Dimethyl. Then cyclo. Octene. No need for a number, obviously, because the alkenes. Obviously, this is the one. 1, 2, 3, 4, 5. Hexene. Sorry, I thought it was 8. It's just 6. So hexene. Yes. Next one. It's this tetrafluoroethene with no numbers, because where else could they go? Where else could they go? All right. 4. A compound has a formula C4H8. Draw 5 possible structures for this. So guys, do you notice straight away it's in the form CnH2n? And when it's in the form CnH2n, what's everyone thinking? Either a cycloalkane or a alkene with 1 double bond. So draw and name 5 possible structures. Here's one. Cyclobutane. Here's another one. I'm being lazy and I'm writing CH3. In your test, you have to draw all the bonds, okay? So what's this? Methyl, cyclopropane. What else is there? 1, 2, 3, 4. Double bond here. What's this called? Butanene. What about this? 1, 2, 3, 4. Double bond here. HH here. All right. Is that different to that? Do you guys notice over here? What are both these things? Are they both hydrogen? This and this are both hydrogen. But what about over here? One's hydrogen and one's something else. So, and then over here, one's a hydrogen and one's something else. So what's allowed here? Cis trans isomerism. What's not allowed here because they're both H? No cis trans isomerism. So what are the two versions of this? Cis butene and trans butene. The question says possible structures. So it's a little bit confusing. Does structures mean structural formula, in which case you just write butene, or do we write like the geometric isomers? Either way, you get what I'm trying to say. All right. We've done all the straight alkenes. What's left? The branched ones. 1, 2, 3. Double one here. Where's the only spot where you can put a branch? In the middle? Nowhere else you can put it. We'll just make it fall big anyway. So, and what do you notice? This thing here is bonded to now, guys. H and H, which means no what? No cis trans isomerism, because that and that are the same thing. Okay. Not to mention on top of that, that this and this are also the same. So definitely no cis trans isomerism. So what's this one called? Methyl propene. That's it. Those are your different possible things you can have. Questions? All right, question 5. Using pentuene and pentane, explain why you can't have cis trans isomerism, why it is that cis trans isomerism exists in the alkene, but not in the alkane. Well, it's pretty straightforward, guys. Just have to show them this. That in pentuene, what's the important thing? That this is a what? What's in the middle? Double bond. And what happens at a double bond? Double bond is what, guys? Double bond is rigid. And what does a double bond being rigid mean? Prevents free rotation around the bond, around or about the bond. And if it prevents free rotation around the bond, therefore, what can you have, guys? Cis trans isomers exist. All right, and such that what, guys? How do they exist? Could you either have hydrogens coming on the same side, or what else? Hydrogens coming off opposite sides. Hydrogens can either come off the same side, or hydrogens can come off the opposite sides. Cis trans isomerisms exist, and I'm going to write hydrogens on the same side would be the cis version of pentuene. And hydrogens on opposite sides would be the trans version of pentuene. Cool? All right, easy. And then obviously, guys, pentane is what, guys? Single bonds. What can you have in single bonds? Free rotations. So then it's not really a new molecule. What I'm trying to say is this, guys, in very, very, very simple terms, I'm trying to say this. So say, for example, you have C double bond to C. I'm trying to say that when you have this, they're different things. You can't just expect that this molecule rotates such that this rotates into this position. It can't. This cannot rotate into that position. It just, so they're different things. However, if you have this, C, C, A, B, C again, whatever, X, Y, Z. What I'm trying to say is this, that this was a double bond, so no free rotation. So they're actually different things. But what I'm saying is that this here is a single bond. And being a single bond, you can actually just have this happening. If you really want, put the A here and put the D here and keep the X here and keep the Z there. So I don't want anyone telling me that, oh, look, these ones, what do you notice? Just to prove a point, I'm just going to write A here. What do you guys notice here? Are the A's on opposite sides? And then what about here? Are they on the same side? And can you have free rotation around this bond to make this just turn into this position? No. So what I'm trying to say is there are different things. However, over here, this is important. Over here, there's your single bond. And what I'm trying to say is you can't be like, oh, look, I don't want anyone telling me that, look, A and A are on opposite sides and A and A are on the same side. Anyone trying to tell me that look, this also has cis trans isomerism because they can either be on the opposite side or the same side? You're wrong, because what is allowed to happen here? Rotation. So this can just rotate into this, this can just rotate into this position and it's the exact same thing. Does that make sense to everyone? So therefore you can't call them two different things because you just twist the molecule here, which is constantly twisting anyway. Okay, that's why alkenes don't have cis trans isomerism, because of that free rotation. The key mark is saying that the double bond is rigid and it prevents free rotation. Okay, let's keep going. That was part A. Part B. Considering this, discuss whether it can have geometric isomerism or not. Well, let's check, guys. Let's see if it can have geometric isomerism or not. Cyclopentene. One, 2, dimethyl. Does that mean there's a C here and a C there? Yes? All right. Well, explain whether this can exhibit geometric isomerism or not. Well, what else could it be? Where else could the C be? Can't be inside the ring, right? And how many bonds are here already? Is there a carbon here? 1, 2, 3, and then 4 bonds. So there only is one atom attached, which means what? Possible to get cis trans isomerism for this? No. That's why I've never seen cis or trans written in front of a cycloalkene, right? So you can explain that each of these carbons, guys, each carbon at the double bond is only bonded to how many? Each carbon at double bond. Oops. How do I say this nicely? Each carbon in the double bond is, I can't say it in any nice words, not possible. No structure, no cis trans isomerism. Okay, can't have cis trans isomerism when it's a cyclic substance like that. All right, next one. Alkanes have the general formula CN H2N plus 2. Write a reaction for an alkane with oxygen in terms of N. Okay, CN H2N. So guys, assuming it's excess oxygen, what are we going to make? Carbon dioxide plus water. What's the difference between excess and limited? What if you have limited oxygen? You make carbon monoxide. Okay, if you have limited oxygen, carbon monoxide, excess oxygen, carbon dioxide. If it doesn't say, then you assume excess. So now I just need to balance this. How do I balance it? N here. N there. So then that's N. That's N plus another. Why do they have to write N's? Okay, NO2 plus another N. So that's like 3N. So then 3N on 2. And then if you want, you can times everything by 2. So what does it become? Cn H2N plus 2, we're timesing it by 2, plus 3NO2 becomes 2NCO2 plus 2NH2O. Yes? I'm pretty sure I could have cheated. I'm pretty sure it was in the notes. Oh, no, that's for nah, they've done it in terms of X's and Y's. Okay, so different question type. But yeah, we're cool with that. Pretty straightforward. Okay. The volume of 1 mole of any gas at STP is 22.71. Can you change that to 22.71? STP's definition has changed since between me being in high school and you guys. STP used to be 25 degrees Celsius, and now STP is 0 degrees Celsius. So that's why they're saying 22.4 there, okay? So the volume of 1 mole of a gas at STP is this. If Y grams of a particular alkane produces X liters of carbon dioxide, you're not going to get a question like this, but anyway, we'll still do it. So guys, how many grams of the particular alkane is there? Y grams. So what's your number of moles of alkane? What is your moles of CnH2n plus 2? Mass divided by molar mass. What is the mass? It even tells you guys. Y grams of alkane. And what's the molar mass? N lots of carbon plus 2N plus 2 lots of hydrogen. Everyone agree that's the number of moles of this? And guys, how much carbon dioxide is produced at STP? X liters. So what's your number of moles of CO2? V divide 22.71. So what would that be, guys? X divided by 22.71. All right. And now, guys, we have to just link all the letters up. That's pretty easy. Can someone tell me how much carbon dioxide is there compared to your alkane? How much? What's the ratio between 2N and 2? This is how much times more? N times more? All right, meaning what? Number of CO2 is N times the number of CnH2n plus 2. And what do you know your number of moles of CO2 is in terms of X? X on 22.71. And what's your number of moles of this? Y divided by that. And there's your answer. It just said find an equation that links your X, Y, and N together. Cool. All right. Weird question, right? But I didn't make it up. All right. Next one. Ethane and ethene can both be converted into chloroethane. Write equation to show the formation of chloroethane. Explain why one method is superior to the other. Okay. So, guys, ethane is a what? Alkane. So if you want an alkane and you want to turn it into chloroethene, what do you have to add to it? Chlorine gas, and you need UV present. And what will it do? Addition or substitution being an alkane? Substitution. So one of them will swap out and become plus HCl. And that's your chloroethane. What else can you do, guys? You can start off with ethene. And if you start off with ethene, what does it do? What do you have to add it to? Not Cl2 this time. What do you have to add it to this time? HCl. And you don't need the UV, right? And all that happens is one will take on the H and one will take on the Cl. That's still chloroethane. Which technique is superior? The addition of HCl to ethene is superior. Why? Higher rate of reaction. Good. Higher rate of reaction. Question number 8. A particular hydrocarbon was analyzed and found to contain this percent by mass. What's the empirical formula? All right. So what you do is this. CH, what's the mass, guys? 85.6% carbon by mass, which means what percentage hydrogen? 14.4. Then you need the moles. All right. How do you get moles? You divide by the molar mass. Who can tell me what's 85.6 divided by its molar mass? 85.6 divided by 12.01. What do we get? 7.127. Okay. And then when we do 14.4 and we divide by its molar mass of 1.008, we get?
14.286.
Great. And now I want the ratio. And to get the ratio, divide both of them by the smallest number. So we divide this by 7.127 and we just get 1. What happens when you do 14.286 divided by that? You should get a pretty much perfect 2. So therefore, guys, what is the empirical formula? Empirical formula is CH2. B. Could the empirical formula also be the molecular formula? No. Why not? It's too small. Yes? Carbon needs at least how many bonds? First of all, what's this generic formula of? You can explain that CH2 is in which form? CN, H2N, right? Which means therefore it's what? Either an alkene or it's an alkene with 1 double bond or cycloalkane. But whether you're cyclic or you're alkene, do you need to link up to something? Therefore, at least how many? I mean, for alkenes, you need at least what? At least 2 carbons. And for cyclic, you need at least how many? 3. You can't have smaller than 3 cyclics, okay? So therefore, at least 2 carbons needed. So if there's at least 2 carbons needed, guys, this is only 1 carbon. So therefore, what are we saying? The empirical formula does not equal the molecular formula. I was very clear about it. I said that it's either an alkene or it's cyclic. And we all should know that alkenes, so why am I saying alkenes need at least 2 carbons to get the double bond between them, and cyclic need at least 3 carbons to get the cycle between them. That's a nice question. Next. All right, so guys, to what group could the compounds belong to? We just discussed it. What 2 groups? Alkene or cycloalkane. I can't be bothered writing that again. 9. There are many structural isomers of C6H12. All right, name 3 of them that are alkenes. And it says structural, so don't worry about the cis trans. What's alkene versions? Keep it boring. Hex, 1-ene. Look how boring I am. Hex, 2-ene. I want to say hex 3-ene. 1, 2, 3, 4, 5, 6. Yep, 1-ene works. 2-ene works. Oh, top one was okay. All right, look at that, guys. That's just me being lazy. So you can have hex 1-ene or hex 2-ene or hex 3-ene. What else could you have had if you decided to change it up a bit? One, two, three, four, five, dump one wherever, and then put a C there or something. So could you have had that? So what's that? 3-methyl, could have even had 2-methyl, but 3-methyl, hex, sorry, not hex, pent, 1E. So many different options. All right, guys, there's so many cyclic versions, right? So that's why it even says cycloalkanes. Give me a few cyclic versions. Cyclohexane, yes. Methyl cyclopentane. All right, I'll just give a few more without drawing them. You could have had methyl cyclopentane, or you could have had ethyl cyclobutane. Why not? Or you could have had 1,3,1,2 dimethyl cyclobutane. Or you could have had 1,3-dimethyl cyclobutane. So you could have had all those things. Yeah, so many. Because they all have, as long as they're, at the end of the day, they're all cyclic and they're all alkanes with 6 carbons. Cool. Which of the following has geometric isomerism? Luckily, we've discussed the exact criteria for how many criteria are there for geometric isomerism? 2 criteria. 1, the double bond to provide the rigidity, and then the different things bonded either side. So let's have a look, see how we go with this. And now we'll just leave the last bit. Okay. So propane. Guys, can we just cancel out anything that says ane? Because they can't have cis-trans isomerism. So let's get rid of ane, and that's it. All right. Now propene. Let's have a look, guys. If I do propene, 1, 2, 3. What do you notice both these guys have? Hydrogen bonded either side, can't be propene. Let's do 1,2-difluoroethene. It's not looking promising, guys. 1, 2, 1, 2 actually, no, take that back. It looks very promising. So H here, H there. As far as I'm concerned, is that different to that? And is this different to this? So then you can have it. So that one can have it. This one's not looking promising. Why? Because it says what? 1,1-dichloro. That means chlorine here and chlorine there. Is that going to work out? Not at all. Okay. This one looks okay. 1-chloro, 2-bromo. C double one to C. Put a chlorine here and put a bromine there. And then obviously this is H and this is H. So we have a winner. No good at all. What do you notice? It says 1, 1. And then on top of that, what? 2, 2. That's as bad as it gets. C double one to C. So there's a chlorine, a bromine here and a bromine there. So you already broken it. And then on top of that, a fluorine here and a fluorine there. Oh, sorry, F is. I even said it is, right? And then I crossed it out, sorry. F is, because there it is. You're going to have cis-trans isomerism. Which other one did we say was good? C, we said was good. All right, what else? Methylpropene, not looking promising. What do you notice? Do you notice over here they didn't write the 1, so they just made a mistake the first time. So what do we notice, guys? Propene, and as soon as they write that, what's coming off? Literally both sides. An H and a H. And on top of that, C on one end and C on the other end. So like bad both ways. And lucky last, 2-bromo-butene. 1, 2, 3, 4. 2-bromo. That looks good. Is this different to this? Yes. And whoops. No, wrong way around. Too many bonds. Is this different to this? Yes. And is this different to that? Yes. So does this have cis-trans isomerism as well? Yes, it does. So there you go. Now you know your criteria for cis-trans isomerism. All right. Oh, almost there. These 3. 2-methylbutene. 1, 2, 3, 4, double bond. Uh-oh. Uh-oh. What do you notice this is? C and C, same thing. Same thing coming off one side, so no good. Let's have a look at the next one. Ethene, 1, 2 dibromo. 1, 2 dichloro. Is this good? Yes, it is. This is good. We have a winner. And hexthrene, I'm sure will work as well. Look. 1, 2, 3, 4, 5, 6. There. H. Is this different to that? Is this different to that? So therefore you have cis-trans isomerism. So what I'm going to do with you guys, the start of next lesson is do the reactions. That's what's left. Some reactions are left and some empirical formula. But you need to watch that one video on the functional groups, okay? I should be well ahead of school.